So operations on functions is the first topic in Unit 4. So today we're starting a new unit. We'll talk about 3 topics today: operations on functions, compositions of functions, and inverse functions. None of those topics will be on next week's exam. So next week we have our exam over Unit 3, and today we're starting Unit 4. So this is sort of a preview of Unit 4. I think that because we're sort of laying the foundation for Unit 4, these topics are a little more elementary than the more complex stuff that we've been doing recently. So I'm hoping that you'll find these 3 topics a little more approachable than the more complicated stuff at the end of Unit 3. So let's get started on operations on functions. The idea here is that we want to take 2 functions and put them together in some way to make a new function. So here I could define the function f plus g, or the function f minus g, or the function f times g, or f divided by g, where f and g are some given functions. So these are all operations like addition, subtraction, multiplication, and division, and each of these is supposed to define a new function in terms of 2 old functions. So let me just give you an example. And let's talk about the most complicated case that you can get, which is a division. So let's say that you have a function f of x that's equal to, let's say, x squared. And then we have another function g of x, which equals x minus 1. Then let's talk about, let's say, compute f over g of x and its domain. So let's talk about these 2 things. First, let's just talk about what f over g would be. So if you need to define, sorry, that's a little messy. If you need to define the quotient f divided by g evaluated at x, thankfully this is nice and simple. F over g is just going to be f of x divided by g of x. So that would be x squared over x minus 1. So in other words, f over g evaluated at x is just defined to be the quotient of f divided by g, like that. And you'll do the same thing to compute, let's say, the sum or the product of 2 functions. You're just multiplying them pointwise. So in other words, you would just take the expression that defines f and the expression that defines g, and you would add them together, or you would take those expressions and multiply them together. So these tend to be relatively straightforward operations. However, talking about the domain of these functions can get a little more complicated. So first, let's just think about these first 3 options. So adding together f plus g, or subtracting or multiplying those. So in order to have a valid input to an expression like this, so let's say we want to have some value for x that we're plugging into f plus g. For that to be a valid input, we would need to know what f of x is, and we would need to know what g of x is. In other words, x needs to belong to the domain of both of these. And the same is true for these other options as well. So in all of these cases, we're going to need, in all of these cases, we need both f of x and g of x to be defined. So the domain of these functions is going to necessarily be the set of points that are in the domain of f intersected with the set of points that are in the domain of g. In other words, you need the common domain between the common points between the 2 domains of the functions. There's one extra trick that shows up, though, whenever you talk about division. So in order for a quotient to be defined, we also have to make sure that this denominator is non-zero, because we're not allowed to divide by 0. So let's look at a function like this one. Here we have f over g of x is supposed to equal x squared divided by x minus 1. In order for a point to be in the domain of f over g, what we need is we need it to be in the domain of f and also in the domain of g. So that was the first thing that I said, which is that x needs to be a valid input for both f and g. But then we need to take away any of the x values such that g of x would be 0. Because if we plugged in that x value, then this denominator here would end up being 0. And then we'd be trying to divide by 0. So let's compute that in this example. So first of all, the domain of f is the domain of x squared, because f was x squared. So that domain would be all of r. The same is true for the domain of g. The domain of x minus 1 is also all real numbers. So the set of points that they have in common would again be all real numbers. So both of these domains are all real numbers. The set of points that they have in common is all real numbers. But we need to take away any point that would cause this denominator to be 0. In other words, we need to take away the roots of this denominator. And in this case, we just have a single linear term in the denominator, it's x minus 1. The thing that would make that 0 would be plugging in an x value of 1. So we would need to take away the point 1. And if you want to write this in interval notation, you can. This would be all real numbers except for 1, which we normally write like this. You would say the interval from negative infinity to 1, and then the interval from 1 to positive infinity like that. So this would be the domain of f over g. So you can use some of these complicated formulas to compute the domain of f over g. You can also instead just compute f over g as a function and then decide what the domain of this expression should be. So notice that the numerator is defined everywhere, the denominator is defined everywhere, but we need to avoid dividing by 0, and therefore the domain would be everything except for the value 1, which is what we have down here. So those are the basic ideas that we'll encounter in operations on functions, and in compositions of functions we'll meet the last